Prateek is principal scientist and director at Google DeepMind. Netflix had a big challenge.
Netflix had a big challenge. NVIDIA had realized that a lot of AI workloads are coming in. So they started investing very heavily in GPUs. Google was a true blue AI company. The search, ad, YouTube, all these products could sort of unlock value because of machine learning and because of AI. Indian parents stress that you should learn your math very carefully, and then rest of the subjects will fall in place. So somehow that seemed to happen for models very naturally.
So one of the debates or maybe criticisms is that, within India, we don't have, you're probably an exception, or your team, but we don't have deep AI research.
So for a country of this size and this diversity, we should not be just consumers or some very, very far away, endpoints of techniques and technologies and models that are built far away.
So if you're a CTO today, right, what, if you're building AI apps, what should you be thinking in terms of your architecture? Hello, everyone. Welcome to Prime Podcast. Today, I'm really excited to welcome Prateek Jain on the podcast. Prateek is principal scientist and director at Google DeepMind. He leads the machine learning and optimization group at Google DeepMind, which puts him right at the frontier of how next gen of AI is being built. He's one of the country's leading researchers. He has PhD from University of Texas at Austin, multiple Best Paper Awards at AI conferences and the ACM India Early Career Researcher Award, as well as the Young Alumnus Award at IIT Kanpur. What's exciting is that he's not just working on making models bigger, but in making them more efficient, scalable, and safe. So in this conversation, we'll dive straight into what's happening in AI right now, how it's evolving in the future, and the big question of whether India can do truly deep AI research, and most importantly, what founders should be doing and avoiding as they build in this really rapidly evolving space. So welcome, Prateek. It's terrific to have you with us.
Thank you so much. Really excited to be here and excited about the discussion.
Absolutely. Let me just launch right into it. So if you look at the AI landscape today, if you could just frame it for us, what is like a quick evolution of AI? Because you have been in it for perhaps 15 years?
20 years.
20 years. Okay. So if you could just give us like a quick history of this field from where you started tracking it to where it is today.
Yeah, it's been one of the most exhilarating experiences, I think. So when I started, actually, I was in college and I was in second year, and I came across this book by a person named Jeffrey Hinton, who had an algorithm named backprop there. It just feel like, some fancy thing. I was in second year, I tried it out and it seemed to work. And it was somewhat interesting, surprising that what's going on here. But I didn't think much of it at that time. I was like, okay, that's fine. And then because I was interested in that book and that kind of work, I ended up enrolling in a machine learning course during my undergrad. And at that time, they used to teach us very basic decision trees and support vector machines. So that was the starting point for me in terms of machine learning journey. Then when I graduated from my undergrad college, I joined UT Austin computer science department, and I wanted to do machine learning, but with little bit more sort of mathematical and rigorous focus. So focus more on things like optimizing machine learning algorithms. So at that time, machine learning was its infancy, machine learning AI. So we had the models were working, but you needed to be an expert to make them work for some very specific tasks, right? So there were people who were experts in sort of creating, say, sentiment classification kind of models, and they would spend a lot of time figuring that out. There were people who were good at figuring out models for tagging, for image classification. But nothing was a given at that time because you needed to handcraft basically the input even that goes into the model, and figure out how to train the model, etc. And at that time the models were also either very simple like linear uh, models, so like support vector machine kind of things, or fair many of them were around decision trees, so fairly simple models, did not require a lot of compute. GPUs were not that much in sort of fashion at that time. So that was sort of the origin. And then as I was sort of working through it, like during my PhD, I focused mainly on the theoretical aspects of statistical learning theory, optimization, things like that. And things were starting to pick up. Like I could sort of get a sense that this field is picking up, like ideas like recommendation systems and retrieval systems, they were picking up. Big chunk of that was thanks to internet and thanks to Google also.
Netflix had a big challenge. You
Netflix had a
remember?
big challenge, and that was actually one challenge that I worked on, and I ended up working on that kind of problem for next 2-3 years. It gave me a plethora of very interesting sort of mathematical problems. So yeah, it was like there was that feeling that this is picking up. People are talking about it. People want to integrate some of these ideas in their products, but it was not a commodity. It was like you have to be a high-end researcher or engineer to go figure out what's going on there, and industry was way behind what academia was at, right? So academia would talk about very fancy techniques, and industry would be taking some very simple things and just applying them. So it felt like, oh, like you wanted to be in more sort of academic research kind of environment.
Difference between academia and industry.
Yeah, so at that time, like as a young sort of graduating researcher, you wanted to be either in pure academia or in sort of blue sky research kind of labs. So I was lucky enough to join Microsoft Research Lab at that time, and continued my journey around learning basics of recommendation systems, doing research there, as well as learning theory, and things like that. And then things all of a sudden changed in about 2011. That's when this AlexNet work that came out from Jeff Hinton's lab. Elias Utzkover was also involved in that. And that was the first time a purely neural network based model was able to do better than fairly carefully designed, like computer vision models for image classification.
This was the big Stanford database of images, right? That was the
that
canonical
that
benchmark.
also came at around similarish time. Yeah. So in fact, like almost like a few months back till then, like people used to use this data set called Caltech 101 and Caltech 256, which were designed at Caltech actually by again Fefeli. So people were hill climbing on those data sets very hard, but most of the techniques were around designing some sort of features for understanding what is going on in the image, and those features were designed by almost by hand. Like a lot of creativity and ingenuity and deep insights from the researchers were required there. And at that time, people treated machine learning as in word of one very famous computer vision researcher as just mumbo jumbo, that you would add it to get your paper accepted, but you would not rely on it. Like the main driving force of most of those models was the features that people would set and design. Right? So that was the thought process at that point of time, that if you have to solve a machine learning problem, it can be solved, but you would need domain experts to sit and design the features. 2011, that changed. They were like this work on AlexNet showed that you don't need to do anything specific. You just give me a bunch of images, and then a neural network will take that image from pixel format all the way to a image classification tag, right? And it was able to beat the state of the art by substantial margin at that point of time. And that essentially opened the floodgates, because people were like, wow, like if this model can do it so well, then let's go and try to do it at a larger scale. Let's try to go and apply it for different problems. So yeah, why only image classification? Let's try it for image segmentation. uh, why only for image segmentation? Why not for, say, object detection and multiple object detection? So for a couple of years, there was a lot of work around convolution neural networks, right? And around that time, like till that point, there was this parallel community that was natural language processing community. That community also had a similarish origin story as computer vision, in the sense that they also had very specific tasks that they would do, say some sort of parsing, semantic tagging, etc. And they would also have their own hand engineered features and very carefully designed models to solve those tasks. Again, machine learning was not giving them a lot of value. It was the task definition, domain definition many times, and the features that was giving that value. But then around 2012, 2013, they were like, why are we being left alone? Why are we behind? So let's also try to apply these models. Now, issue was that convolution neural networks look much more natural for images. So around that time, then people started picking up things like recurrent neural networks or LSTMs, which felt a lot more natural for text. And around that time, there were multiple very influential works came out. One was from Google, Oriel Vinyals and Quackley, and a bunch of co-authors who came up with this idea of sequence to sequence, where they were like, if I need to do translation rather than going through more traditional translation pipelines, which are fairly challenging, maybe what I can do is I can take this input sequence, and then the output of that input sequence should be another sequence that means essentially the same but in a different language. So I will need parallel corpora of two languages, same sort of sentence written in two different languages, but I will use my recurrent neural network, or some neural network, to translate this sequence from one language to another. So that was then the start of serious deep learning effort in natural language processing world. Also around that time, this very famous work called Word2Vec also came through, where the idea was to start representing words, and then later on the context of the words in terms of vectors that can then be consumed by your machine learning models. So that also then started to get rid of this design of features by hand, but using these existing machine learning models to actually get you the features that then downstream machine learning models can use to solve whatever retrieval, recommendation tasks, etc. So that was happening, and 20 very very fast moving world. It was so 2014, 2015, people were scaling the models all the time. There was this residual connection and ResNet line of work that was able to show that you don't have to stick with 5-layer, 10-layer deep models. You can go to even 100-layer deep models. Until that point, also, you can keep on getting value. That is, even on the computer vision benchmarks, compared to, say, a 5-layer model, if you go to, let's say, 100-layer model, you can get significant quality bump. So people were doing all sort of crazy things at that time, and things were moving very rapidly. There was significant dent in the natural language processing world also, but the things were getting bit saturated there, because we were getting stuck by the training cost, right? That is, these recurrent neural networks are sort of sequential um, neural network machines, which means that when you want to train them, you have to train them in sequence. One word at a time will be processed during the training phase, and that can be super slow. So that was sort of holding the whole enterprise back. But that's when this very famous legendary sort of 2017 paper on transformers came out. We said that, oh, you actually don't need to do the sequential thing. There is something called attention. That is all you need. The attention was already used actually in the standard recurrent neural networks, but they said that, okay, I don't care for the recurrent part, I just need the attention part, and that can then allow us to train models on very large corporas very fast, because a lot of parallel processing was unlocked. And at that time anyways, a lot of work on hardware had started. So GPUs were becoming more and more powerful. NVIDIA had realized that a lot of AI workloads are coming in. So they started investing very heavily in GPUs. And on Google side, like the visionaries in Google leadership started investing in TPUs because they were also able to see that these AI workloads are going to become very important. And in particular for Google, because Google was a true blue AI company, the search, ad, YouTube, all these products could sort of unlock value because of machine learning and because of AI. So they were investing very heavily in the hardware in TPUs. So hardware was also coming along, and then this new algorithmic innovation came through, which could now allow us to take a lot of data and scale models to like really really gigantic sizes. So for next few years, that's what was happening. Like for 2 3 years, people were coming up with bigger and bigger models. They were doing this mass language kind of modeling, and BERT models became very popular. They were used very heavily within Google for retrieval ranking kind of problems, and I think across industry also they became almost household name. A lot of companies were using either standard BERT models or training their own BERT models. So that was going pretty well. But then around 2020, another sort of big sort of step jump happened, which is that people realized that A, we can train these models on like entire internet data, and B, we can sort of do few shot prompting of the model. So I don't have to train or fine tune my model for individual tasks. I can just do prompting of the model and solve my task. So few shot prompting,
basically giving context.
giving context, and model can understand the context and it can solve the task. So that then like picked up, and then the 2022 or like this ChatGPT moment happened, where people realized that putting these models in the hand of customers or consumers can sort of unlock very interesting sort of capabilities. People are able to use them in a variety of very interesting ways, and then people realize that, oh, maybe we can use them for coding also, we can use them for our customer service problems also. So all sorts of use cases started to flood the market. And on the modeling side, the scaling game was continuing, the data game was continuing. That is, let's put more data, let's put more scale, let's put more compute, and we were seeing value. And then about 6 to 8 months back, another sort of paradigm shift happened, which was around thinking and very long RL, where people were able to figure out that if we can run very long RL and let models think for a lot of time, it is indeed able to sort of solve very interesting, very hard problems as hard as like international mathematics Olympiad problems. And yeah, lo and beyond, like that's where we are, where yeah, like models have become fairly capable. They are able to understand natural language very, very well. They are multimodal. They are able to do fairly intricate reasoning. They are able to solve a lot of very hard code problems, reasoning problems. Looking very interesting.
And that's fascinating an evolution story. The just from a terminology standpoint, do you distinguish between, and how do you distinguish between ML and the generative models, right? The LLMs, etc. Like, how should we think about it?
So ML is a little bit more broader term, I would say, because ML would then contain, or like people like ML experts or ML researchers would work not only on large language models, but they can also work on other type of models like decision tree type of models, or say previous eras like recurrent models, convolution models, as well as understanding the basics behind all these models. So understanding how we can train these models efficiently, uh, what should be the statistical learning theory behind these models, how we can explain what's going on here, and how we can use statistical learning theory to design new better models that are more reliable. So ML, I would say, sort of encompasses
Catch
a
all
bit
term.
more terms.
So, is there actually a difference between the previous era of models pre the LLMs, right, and the ones which are now, where basically all the LLM based models we are seeing, in terms of how deterministic the answers were? Did they tend to be more deterministic, or was this level of sort of probabilistic nature to the answer always a part of all of these AI models?
Great question. So generally, like when we had earlier our classification or tagging or discriminative tasks, models were fairly discriminative, fairly deterministic. That is, they would tend to sort of give one answer. Now, there was a lot of work in Bayesian and like variational Bayes and Bayes optimization community, where they would talk about not only giving one answer or one tag, but giving a distribution over it, right? So if I show you an image, you would sort of say that, okay, with 50% probability, I say human here, with 25% probability, I see a table here, and so on. So they were already working on this sort of probabilistic models. But I would say that most of the classification or tagging tasks were fairly deterministic. Uh, the generative models or the clustering kind of models and all, they tended to have a lot more probabilistic sense to them, probabilistic things going on for them, because one of the goal of generative model is to generate new data points. So because of that, you would want some randomness inbuilt in them. LLMs are a very unique thing where in some sense they are trained as with like the standard classification or tagging kind of thing, but they are used for generation. So when we are training them, in some sense we are trying to make sure that we can get at least some interpretable probability distribution from them, and then use that probability distribution to sample data points or
So in one
sample
sense, it's
answer.
actually the application which has led to, inherently being probabilistic, right?
Yeah.
Because they're not being used for that. They're just kind of like stopping it at the classification previously.
Yeah.
So if I were to say, like in the last year, this field is of course evolving very rapidly, as you mentioned. What was the one thing which surprised you in terms of where we are today versus, roll the clock back to 2024 August?
Mhm.
Uh,
I would say the efficacy of long reinforcement learning has been super surprising, because about a year back or so, many times people were also questioning whether do we even need any reinforcement learning. People are talking about, like, do we need RLHF and techniques like this, or can we just get by with standard supervised tuning, fine tuning. So give model a bunch of question answers and just run some sort of supervised fine tuning, and that might be enough for it. But what happened was that RL came in and showed that if you can sort of think a lot over some problem, if you as in a model, and then produce an answer, and if that answer can be verified deterministically, right? That is, if a model can look at that answer and say that, oh, this is a right answer or this is a wrong answer, which
okay,
is
some kind of reward.
yeah,
There, yeah,
yeah, like a deterministic reward function, which is very common in math or reasoning,
yeah.
or other problems. They Once they figured that out, they sort of started to apply this long reinforcement learning, and they started to sort of just scale reinforcement learning more and more. And the surprising part was that models kept on learning more and more. And one interesting thing that I always find is that folks found out that if we run a lot of reinforcement learning on, say, some math problems and all, then the models start to become good overall in general. That is, they started to do better reasoning overall in general,
Better analytical
better
abilities.
analytical abilities, which seemed very similar to what I guess at least Indian parents
Yeah.
stress that you should learn your math very carefully,
Yeah.
and then rest of the subjects will fall in place. So somehow that seemed to happen for models very naturally.
That's
Um,
fascinating. So, what are the biggest bottlenecks today, you think, in terms of, there are all these areas, like there is, of course, the talk about data, and there's also compute, and there's this alignment, all these kind of like other issues. So where do you see the current bottlenecks, of course, which people are going to be working on
yeah.
in further evolution of the data model?
Yeah, so I can think of a few. So one obviously is that the models currently are autoregressive, which means that they produce one word or one token at a time.
Hmm.
So they have a sequential nature to them, which then makes utilizing our this very fast parallel accelerators in a very deep manner. So thinking of techniques like maybe diffusion models that can get over that hump, like that seems pretty important. Then other is around data, which is that as we are getting more and more capable at training larger scale models, we might be running out of the data that we can train our models on. So figuring out more data sources, a, and also figuring out maybe if we can have say synthetic data sources to augment our code training. That might be another sort of very interesting direction. And another is like figuring out if we can look inside the models a bit better and understand certain failure cases and try to fix them. That would also be very interesting. That is, we routinely come across various scenarios where models does very silly thing, like model which is as powerful as one that can win I am a gold medal many times also does very silly mistakes. And right now it's not very clear where that originates from, how we can fix them. So that opaqueness in the models is a problem, and figuring that out is important, especially because as these models become more powerful, more used, there is also a severe risk that they will be used by bad actors. And making sure that models cannot be used by these bad actors, so telling them that hey, these are your instructions, you should follow them, you should not fall prey to attacks and poisoning and jailbreaks from bad actors, that become very important. And for that, again, understanding what's going on inside the model might be critical.
So the observability and ability to audit and all those kind of things,
Yeah.
right? And it feels like the larger the models you make, this is going to be a fairly complex problem to solve here.
Yeah, one of the big challenges that I think remains that we need to sort of get. Yeah.
Okay, let me change our topics here, which is moving to the context in India, right? So one of the debates or maybe criticisms is that within India we don't have. You're probably an exception, or your team, but we don't have deep AI research, right? That's happening elsewhere. You're seeing models coming out of the US. You're seeing the whole DeepSeek thing and distilled models, and then new models of other open source stuff coming out of China. So, one, what are your points of view on that? And second, that more importantly, I guess, do we need to think about our AI capabilities in from that framework, or how should we think about it? About developing, India becoming a AI superpower on the tech side.
Yeah, no, that's a great question. And yeah, I tend to think about that quite a bit, and I don't really have very good answer, I would say. I don't claim to also understand the Indian ecosystem very, very deeply. But like just based on some observations, the one thing which is very clear is that AI and like these large models and foundation models, they are going to go and affect pretty much every aspect of our life, right? So how we work, it's like no, it's already happening. Like our coding and the note taking and organization, like a lot of those things are changing very rapidly thanks to AI. Similarly, concepts of digital assistants and tools that can help us be more productive and more effective, and do better job of not just at work but also with our family and life in general is becoming important. In education, it's going to become very, very important. Healthcare. So pretty much every aspect of our life, it will be touched by AI. So for a country of this size and this diversity, uh, we should not be just consumers, or some very, very far away endpoints of techniques and technologies and models that are built far away, right? Like we should be getting that expertise built in house. Like it is very, very critical. And India, has been really, really good at fundamentals, right? I mean, we have a pretty big base of engineers and researchers, mathematicians, academics, right? So we want to make sure that we uh, sort of, build very, very strong foundations for people to learn and people to sort of execute on various things that are needed for building AI products, AI solutions that can sort of have impact on billions of people, right? So because of that, I feel like we need to not just think about, oh, can I build the latest model which is at the frontier of the models. It is also about building that base, right? So for example, like the way 20, 25 years, 30 years back, we built a base of very strong engineers who were very fluent in, say, English, and who could sort of
Mm.
operate it as global citizens or global engineers. I think we need to do the same for AI. We need to build a very strong base of AI engineers, AI app developers, AI researchers. That is like for sure. And along with that, as we build that, I'm sure like we will be building our own models and figuring out innovations and adding our own spin to a lot of this work.
And I suppose open source will be a big part of it, right? So I think, in one sense, we could, I feel, become very good at leveraging the current state of the art in open source and then developing more stuff on top of it. Because in one sense, you could argue we don't have the compute capacity to just, deploy all these things. It's a massive capital investment, I guess, and also access.
Yeah.
So does open source really help there in terms of accelerating our access to building these kind of things?
Definitely, I think open source helps a lot. We don't need to start from scratch. We can start from that. But as I was hinting earlier, right? Like many times the bottleneck is not the model. Many times the
Mm.
bottleneck is as you mentioned, the compute, but also our human resources. That is, we are lacking, I think, significantly in terms of very deep AI infrastructure talent, AI engineering talent. So I think building that up also is very, very critical. And I feel very bullish because building fundamentals has been especially in the human resources world, has been a strong suit of India. So we should sort of invest very heavily in it and build it along with the compute and building models and that will we should do. But I think having our fundamentals in terms of our human resources is also very critical.
So if you look at the future here, now I'm kind of like asking you to look into a crystal ball a little bit, say 2, 3 years down the road, not too long, not too far out. How do you see, this model universe? So there will be, of course, right now the foundational models have sort of consolidated, right? There are the big players there. There are a couple of open source things out there, and then we are beginning to see, some maybe some small special purpose models out there. So if I were to say, 2, 3 years down the road, like how do you see this landscape evolving? Will there be, let me just say, like, yeah, 3 or 4 of these foundational models, but hundreds of other models which people are using for all these different kind of things? Or it'll be more like, the OS world, right? Where we had 2 or 3 operating systems and then everything sort of like coalesces around that.
It's a pretty interesting question, hard question to answer. Like based on things that we have seen so far and trend, it does seem like we will be moving little bit more towards consolidated models world. Uh, Again, it will not be like there is only one model. Like there'll be a family of models, but still there would not be a lot of custom built models for specific use cases. um, because the issue with those custom built use models is that you have to invest significant sort of human resources around it, and then many times you might not even know how your use case evolves, and the ability of bringing in all the world knowledge into your use case, what all it can unlock. So because of that, it seems to me, at least, like, and I would obviously have more biased view because I come from a sort of, so-called frontier lab, but generally it seems like people are coalescing towards taking, like, pre-built models that have a lot of power. You would need to select a model that fits your use case. Like, so you would not use, let's say, a Gemini 2.5 Pro for a task which is relatively simple and where you are very cost or latency conscious. You would select a more appropriate model for that work. But rather than training that model from scratch, etc., what you would want to do is take that model, try to prompt it in various ways. If you need to add more information in the model, you can add that information by adding it in the prompt of the model. Nowadays, models are supporting, like, very long context. So, for example, Gemini, we have, like, context length support of 1 million to 2 million. So you can put in a lot of information in the context, and models are becoming very, very good at understanding whatever is there in their context very well. So I think, rather than building a lot of custom built things, it would be very strong models across the sizes, so that, like, you can meet your latency or cost requirement. But then doing better prompting, better sort of, adding information in the context. Those are the type of things that will sort of take off.
So one related area, of course, is around these edge models, right? Devices, models which can run on
Yeah.
the phone and things like that. So do you see that in the next 1 or 2 years becoming a lot more accessible and powerful,
Yeah.
smaller, power efficient?
Definitely, right. So, I can give you one example. So, just during May this year, we from Google DeepMind had released Gemma 3N model, and it's a very small, like 4 billion parameter model. Within which another sort of smaller 2 billion parameter model is nested. And when you look at the capability of these models, they actually are able to rival the capability of the largest, like the pro size models of, like, 2 generations back, 3 generations back. So they have come a long way. Like, those models have become fairly powerful. People are doing a lot of research and figuring out how we can put in a lot of information in these very small number of parameters, how we can make these models run faster on the devices. Now, one more sort of thing that will keep on evolving is that these devices will also become more and more powerful, because more and more powerful, like, accelerator
Compute is
chips
there.
and
Yeah.
compute will come. Then will also be like, my expectation is that we'll be also be able to add a lot of adaptivity to these models, so that they can run at a fairly power efficient manner on these devices. So, for example, even the Gemma 3N model, we have a 4B model within which there is another 2B model sitting. So if you have a task which is very complicated, you can use the full 4B model. But if you have an easy task, you can just use the 2B model. So you are getting 50% saving in cost and latency and power. So those are the type of things people will be able to sort of, exploit and work on. So basically, bringing in more efficiency and more adaptivity to the edge devices, along with making the hardware
So in
better.
sense, the connectivity requirement will sort of go away, right?
Mhm.
When that happens, because applications can then work directly on the device.
Directly. And what I feel is, what's going to happen is that, uh, rather than competing with the cloud models, in some sense these models will be working as a friend. That is, even if there is connectivity, what will happen is these models will do their own work up to some extent, and if there's certain things that they cannot do, they would know that, oh, this is something that I should send
Do.
it to my cloud counterpart. And also different kind of use cases will be unlocked. So maybe some very low latency, low power kind of use cases that you would want on your phone, for which you cannot sort of call these very expensive models over the network. Those are, or because of privacy reasons also, maybe. So those are the use cases that will be unlocked more and more on the phone. So yeah, I'm definitely hoping that your phone will become a, like, really sort of, strong companion and assistant, and help for achieving the best you can, like, during your day.
So from a founder perspective, right? Yeah, most of our audience is entrepreneurs and those who are looking to start companies. So if you're a CTO today, right, what if you're building AI apps, what should you be thinking in terms of your architecture? If you were to tell them like some directional guidance, right,
Mhm.
what should you be not thinking about, and what should you be thinking about in terms of designing these products?
Mhm. Another very good question. I feel like what you have to think about is that these models have been improving at an exponential rate.
Mm-hmm.
So you would want to think that how this landscape will look like in say 6 months to a year, or maybe 2 years point of view, and use that information in figuring out the problem that you want to solve as well as how you want to go about solving it, right? So for example, let's say if your approach is that okay, currently say Gemini 2.5 Pro costs xx dollars, I can get similarish quality for a very specific domain at half the cost by doing a lot of extra effort and engineering work. Then that might not be a very
Mm-hmm.
good investment, because in 3 months to 6 months, because of just generally chips cost going down, as well as like models becoming better across the board, like at half or one fourth or even say one eighth the cost, you will be able to get better quality models. So if you, so your moat or your differentiator will very quickly evaporate if that's the type of sort of setting you are working in. Similarly, if you are sort of designing your solution around saying that okay, currently these models are not able to solve this task, even though the information about the task is available in public,
Mm-hmm.
but still they are not able to solve it for some reason. And then I will go and try to sort of design my technique, maybe design some sort of workflow, or fine tune the model, or design some other techniques to solve that problem. Again, there is a big risk that in 3 to 6 months these models will evolve and will be able to solve those general tasks. So building your technique or building your solution around that kind of hypothesis becomes very risky. But on the other hand, if you are thinking that okay, in 3 months or 1 year, I expect these models to have these capabilities. Maybe they can become this good at multi-model, this good at audio, this good at reasoning, and anticipate that this is what new product I can build based on that capability. That probably is going to sort of work much better in long term, because then you are becoming an ally to this very rapid progress that is happening, rather than being always been a worry that tomorrow if a new model comes that is able to sort of move the frontier in a significant fashion, then my work will become obsolete.
And so maybe a related point there, Prateek, is that right now we are when we talk to startups and they're doing in verticals, especially very specific problems and getting a high degree of accuracy because it's what the customers demand, is using different models for doing different tasks, right? So if you have some kind of a query or one set of queries, I might actually go to this model because it seems to do well. It's got a lower latency, it does all this kind of things, and it's a simpler query. Let's for the moment say. And then there is this other set which requires more thinking. Let me actually go and siphon it to this side out there. It's doing this. But can I extrapolate from what you're saying that if the general purpose models are really going to become better and better, then maybe they will, this particular level of the routing, so to speak,
Yeah.
it will be inside it itself, right? Just
Yeah.
maybe taking extension of that for the gamma model
Yeah.
which you talked about.
Precisely. So, I mean, so we have been proponing this elastic models quite a bit. We have been doing a fair bit of research on it. We have a technique called matformers or Matryoshka transformers, which is able to bring in a lot of this flexibility and elasticity in the models,
Hmm.
so that if you have an easy problem, maybe we can activate only small part of the model and solve it. And if I need to sort of solve a harder problem, I want to activate larger part of the model. And now with this inference time compute or thinking, this becomes even more interesting, because now what I can do is I can take a smaller part of the model and think for a lot more, and then use a larger model to verify some of that thinking and give the final response. So a lot more fungibility and adaptivity can come into picture. And definitely exploiting this in appropriately in the best manner would be a significant frontier that would want to cross in next few months or years.
So in one sense, you have to kind of like move your differentiation as a startup not in terms of optimizing the model or the interplay between the models or multiplexing between them, as the case may be, but really on stuff which is sitting on top of them and which is, I guess, modular and adaptable enough to work with the changing capabilities of the underlying models, right? Your architectures should be built that way.
Yeah, that is ideally, like whatever domain you pick, you should understand that domain's workflow very well. And if you can design a architecture or a workflow that can exploit that, like, domain workflow, that then you'll be in a good shape. And the other thing is that if you see that your workflows, like in the domain, are very complicated and they might not be present in the general models, then upstreaming some of that data back into the models through post training, or maybe
Mm.
even say some sort of mid training, that might also be quite useful. But again, like, you would want to do those kind of things after exploring all the options and, like, being very, very careful. But definitely, like, understanding the deep depth of your domain, your workflows, and then figuring out what is the simplest solution that I can come up with to solve that workflow, that should sort of place you in a very good shape.
I mean, one analogy which comes to my mind is that back in 2010, 2012, in that time frame, when you're looking at cloud applications, the bandwidth was a big issue, essentially over the air. And so you'd be doing all kinds of optimizations to make sure that this application works and the latency is okay. But really, the right worldview in building apps at that point would have been that the broadband will come, and I don't need to actually spend all my energies doing that, because in a few years' time, I can safely presume that this is going to accommodate a fairly good connectivity, right?
Yeah. Precisely, I completely agree. And here, it's not just the models are coming and becoming better. The techniques that are being used to build those models and, like,
Mm.
modify those models, they will also become better and better, and they will also become more and more commoditized. So you don't need to spend a lot of time also struggling with, say, current techniques, which might be flaky or might be breaking. And, like, rather than that, like, you can safely imagine that in 3 to 6 months, a lot of these things will become better and commoditized, and you can directly try to use that. So
So, what kind of team structure works best? I mean, what is, yeah, we know folks, you need folks, of course, who can understand and are keeping up with the evolution and developments in the model. But what role does, regular symbolic logic, play in terms of creating the frameworks and engineering around these models?
Um, I think they have a pretty important role to play, because despite all the progress, models are still not 100% there, and they can still make mistakes, and they, like, might not have the full world view, right, that you are operating in. So which means that, like, orchestrating the models properly around the symbolic frameworks become important. So some bit of the symbolic framework, maybe you can even give as part of the context to the model,
Mm.
or you sort of say that, okay, my model, I'm presuming, will do this task, and then I will chain multiple models together to then finally execute on the final, like, symbolic task that I care for. Or in some cases, I might even upstream that data. That is, once I sort of collect some data around this, I upstream that data into my post training to sort of have model understands that symbolic workflow innately, and, like, directly work on it. So those are the type of things I think that we will need to converge towards. um,
It's in one sense, actually, the architecture and the nature of building products is going to fundamentally change, because what you're saying is that there's this self, optimizing kind of
yeah,
architecture, right?
yeah,
Because you're doing some things up here, but once you actually have enough data, you want to push it down because it's always going to get done better in the model layer,
yeah.
and then suitably adapt yourself at the top.
Totally agree. Yeah. So you can try to sort of view the whole thing as some sort of, like, optimization game, and where the model itself can help you optimize your workflow. So you can sort of, as long as you're instrumenting things properly and setting your evals properly, you can figure out that, okay, this is a good case, this is a bad case, and try to sort of then improve the models by putting this information back in the model through prompts or upstreaming, whatever. So there are various ways, but definitely you don't need to assume that this is one single workflow which is static. You can sort of continue to improve upon it.
Well, let me, close with a couple of, very quick questions, and you can give me your quick answers to them, which is one metric that is overlooked in evaluating models in model use today, in your opinion?
Hmm. It's a great question. I'm thinking this through. Um, I would say that uh, having a uh, clear cut metrics on if the model is following the instruction properly,
Hmm.
and what is the cost at which it is following the instruction. That is, what is the cost of running one LLM call, but also how much thinking tokens I need to generate to follow that instruction or follow that task. So that sort of metric, I think, I still are not that much popular. You would hear a lot about standard benchmarks and saying that, oh, I achieved this much on bench, etc. But you also need to carefully look at that to solve that task. A, how much instruction following was there, and B, how much tokens I needed to spend and how much compute I needed to spend to get to that solution.
It's a great point you mentioned, because I recall actually reading somewhere that there was a startup which was using one of these, creating an app and using one of these underlying models, which of course charged by usage and number of tokens, and they're just doing fine until one fine day they got a $100,000 bill because this task just went off on its own and then consumed all these tokens, and even the service provider, which is actually billing them, was happily billing them. I don't know whether they recovered their money or not, but it can, things might be going just fine, but one case which you have not overlooked, unless you have rate limiting and a careful guardrails there, and maybe the symbolic framework there can help, can really put things off. So if you had to give Indian founders one piece of advice which you think would be relevant even 5 years from now as they're building AI apps, what might that be?
I would say that build core AI infrastructure muscle. That would be handy no matter what, I think. So, play that long game for sure. And the second thing is that you should try to align with the trend or the improvement and upskilling of the models, um, rather than trying to sort of go in the opposite direction.
Make that a tailwind. And finally, like one paper, book or resource you think every founder should read?
That's a great question. I would say there is a very interesting book by my colleagues at DeepMind, Jacob Austin, and various co-authors around how large-scale LLMs can be scaled across TPUs and GPUs. So that's very illuminating book because it tells you that models that you're using underneath them, what is going on, how are they being laid out on the hardware that we are using, that can sort of help ensure that when things are failing, things are not working as we expect, we can sort of figure out how to fix them. So that's one. Another would be, um, I don't have a very precise reference here, but there are a few works that talk about um, RLHF and RL with verified rewards. Reading those is important. And finally, I think the DeepSeek paper was very interesting. It laid down a lot of very interesting sort of ideas, and provided wrote them in a fair bit of detail. So I think understanding the DeepSeek paper is also important.
Well, thank you, Prateek. I won't take too much more of your time. It is just terrific having you here, and honestly, it's just so exciting, and and motivating to see that, folks like yourself who are doing cutting edge research on the frontier models, doing it right here in India. So I'm very optimistic about what the future holds for us. Thank you for
Yeah.
being with us.
Dear listeners, thank you for listening to this episode of the podcast. Subscribe now on your favorite podcast app for free, and you'll be the first one to know when new episodes are available. Just search for Prime Venture Partners Podcast in Apple Podcast, Spotify, Castbox, or however you get your podcasts. Then hit subscribe. And if you have enjoyed the show, we would be really grateful if you leave us a review on Apple Podcast. To read the full transcript, find the link in the show notes.